In the final part of the lecture, I want to discuss another extension of PCA to kernels. This is a technique called kernel PCA. And so we've seen how when we have an algorithm that uses dot products, so if we have an algorithm that is represented purely in terms of the dot products of our data points, then we can generalize the algorithm by replacing the dot products with a kernel. This same exact generalization can be made with PCA. So let's see how that's done. So recall with PCA that what we do is we take each data point xi, we take its outer product, so we haven't gotten to the inner products yet, so we take the outer product of that data point with itself and sum them up and represent that as this matrix product. So so the matrix X had each xi along its column. We took X transpose, and then we found the eigenvectors of this matrix. So now let's map the data to higher dimensions. So it's funny that we're discussing a dimensionality reduction technique, and now we're going to map the data to even higher dimensions before doing dimensionality reduction. But hopefully in later slides it'll be very convincing that this is actually a smart thing to do. That actually projecting to much higher dimensions before projecting to a much lower dimension can do even more for us. So let's let this phi, as usual, be our projection of the data point x to a much higher dimension, from D to capital D, where capital D is much greater than little d. And now with this higher dimensional projection, what we want to do is learn the eigendecomposition of this. So notice originally we wanted the eigendecomposition of the sum of these outer products, which we saw could be represented as constructing this matrix. So in a previous slide we showed how we can take this matrix times an eigenvector q, and that's equal to the kth eigenvalue times the kth eigenvector. So previously we didn't use the subscript k. However, there are k of these pairs. There are many of these pairs that we can learn, and we sort them by decreasing order in terms of lambda. So now we want to find the vector q and the eigenvalue lambda for the matrix from this higher dimensional projection. So instead of having this original dimensional data, we project it to higher dimensions and we have this problem. So now how can we do PCA in this higher dimensional space? How can we learn q and lambda in an even higher dimensional space? For example, with Gaussian kernels, this is an infinite dimensional space. So we want to see how we can sidestep that issue. So here's where some of the sleights of hand come into play, the tricks, the mathematical things that we can do to fix this problem. So let's just reorganize the operations of the eigendecomposition. So all I've done is taken the previous slide. Remember, lambda k was originally multiplied against the kth eigenvector. Now I'm bringing lambda k onto the left side by dividing it. So I've divided both sides by lambda k. And also originally on the previous slide, so I divided both sides by lambda k. Also originally, I viewed this term first. I completed this term first and then multiplied by qk. Now I want to switch the orders. I want to multiply my higher dimensional projection of xi with the kth eigenvector divided by the kth eigenvalue. And now I'm going to call that a sub ki. So I is indexing the data point, k is indexing the eigenvalue in the eigenvector pair. So now notice that what I've done, and it's not clear why this will help me yet, but what I've done is shown that I can actually represent each data point, I can actually represent each eigenvector qk as a linear combination of my data projected into the higher dimensional space. So I can take my ith data point, projected it to the higher dimensional space, multiply it by aki, where I is paired with the data point, sum it over each of my n data points, and that's my kth eigenvector. So I've just shown that there exists some value for a ki such that I can represent it like this. And now I'm going to write AK as a vector in Rn. So AK now corresponds to the kth eigenvector QK, and it's an n-dimensional vector where n is the same dimension as the number of data points that I have. So now there's the trick comes into play, where instead of learning QK, we're going to learn AK. So instead of learning this potentially infinite dimensional vector, we're going to learn an n-dimensional vector corresponding to the kth eigenvector. Okay, so how do we do this? So let's now take QK out, and let's replace it with this representation of it. So QK appears up here. What we're going to do is we're going to take QK out of both of these terms, and we're going to replace it with this term right here. And we're going to bring lambda k back over to the right-hand side, and we end up with something that looks like this. So it looks more complicated, but eventually it's going to make our problem even easier. And so now notice that we have finally the dot products we're looking for. We took this value for this representation of QK and put it here, and brought lambda k back over here, and we have dot products. And so here's the first place where we can take these dot products of the higher dimensional mapping and replace them with our kernel function between the ith and the jth data point. So we're making some progress. The next step is to multiply the left and the right-hand side both by the projection of the nth data point for each of the n data points. So we take this vector phi of xl, it's a capital D-dimensional vector corresponding to the nth data point, and we construct a matrix where we have this along the nth column of that matrix. So in a sense, what we can say is we're making a big matrix phi, which is equal to the matrix of phi of x1 to phi of xn. And now we multiply phi transpose against both sides, like this. And now we're going to see that that's going to simplify our problem. So when we take each of these higher dimensional mappings, transpose it, and multiply it on both sides of this equality, we're going to end up also with an equality that looks like this. And so here's where we were able to introduce one kernel by multiplying this on the left side of both of these sides. We're going to get the other kernel. And so I'm not going to work it all out in mathematical detail, but what you can see is that when you do that multiplication, when you could construct that matrix phi, which is again phi of x1 to phi of xn, and you take phi transpose, multiply it by both sides like this, you get this equality. You get the kernel matrix squared times AK equals lambda k times the kernel matrix AK. And so now the kernel matrix K is an n by n matrix constructed on the data. So Kij is the kernel between data point xi and data point xj. Now let's multiply both sides by the inverse of K, which is a positive definite matrix, and we get this equality. So we've done a lot of work. Perhaps it's not clear, how this relates to the original problem. Maybe it's a bit too many steps, but we can work through it and find that equivalently we want to find this eigen decomposition problem. Notice that we're taking the matrix kernel K now. It's n by n, and it's that kernel times the vector AK is equal to the eigenvalue lambda k times the same vector AK. So what we've shown, without ever really solving it, we've shown that this AK that we've defined on a previous slide here, we defined this to be AK, is now the eigenvector associated, the kth eigenvector associated with the kernel matrix constructed among my data. And so again, originally I could have mapped the data into such a high dimensional space, like an infinite dimensional space, and now I'm representing it as a eigendecomposition of an n by n matrix, where n is the size of my data. So in short, what kernel PCA does is it takes in the data, x1 through xn, so our n data points, each one is an RD. It defines a kernel function between all the data points. For example, the Gaussian kernel could be this one, so Kij would be the kernel between observation xi and xj, which is equal to this equation here if we use the Gaussian kernel. We construct this kernel matrix on our data, an n by n matrix, so it's pairwise between all of our data points. And then we solve this eigendecomposition by calling the function built into our program, whatever programming language we're using, to get the eigenvector and the eigenvalue for that kernel matrix. And we do it for the first r eigenvalues and eigenvector pairs, whatever r is. So r is the dimensionality we want to project the data into. If we want to project it into 3 dimensions, then r is equal to 3. We get the first 3 eigenvalues and eigenvectors of the kernel matrix K. And now we output a new coordinate system where we've taken our vector xi. Implicitly, we've mapped it up into this high dimensional space and learned r different eigenvectors there in that higher dimensional space, and then projected that data back down into the lower dimensional r dimensional space. But if you go back and look at the derivation, this projection is equal to this. So we learn for the kth dimension of our projection, we learn the kth eigenvector and eigenvalue. And then for the ith data point, we look at the ith dimension of the kth eigenvector and multiply it. So the first dimension will be the ith dimension of the first eigenvector of k times the first eigenvalue, and so on. And this is our low-dimensional mapping. So before I show this on an example, an immediate question is, how do we handle new data? So if a new x0 comes in, how do we project that into the lower dimensional space using exactly the same assumptions as the model was using? So before, what we did, if you recall, is we learned the eigenvectors. For example, if we wanted to project using the kth eigenvector qk, we simply took the new data point x0 and multiplied it by qk, and that's now equal to the kth dimension of the lower dimensional projection. And so we had k equals 1 to r. We did that dot product r times. That's our r dimensional projection. But now alpha ak is different here. So how do we project data in this case? So first, let's recall the relationship of the vector ak with the eigenvector qk in kernel PCA. So we showed that the kth eigenvector in the higher dimensional space can be written as aki. So the k is indexing the eigenvector, I is indexing the data point. So aki times the vector we get by mapping xi to a higher dimension, and then summed over all of our data points. And then we use the kernel trick to avoid having to work with or even define any of these higher dimensional projections. We realize we can have only dot product representations and just use the kernel function. So now, as with regular PCA, after we map x0, the new data point, to the same higher dimensional space, we want to project it into the eigenvectors. So we take x0, map it into the higher dimensional space by the function phi, take the dot product then of that higher dimensional mapping with the first eigenvector, and that becomes our first dimension in the lower dimensional space. And we do that r times to get our r-dimensional projection. But now if we plug in for each of these q's, if we pick the kth dimension in here, so qk, and we plug in what this is equal to, so this dot product will equal the kth dimension in this projection. But now we take this and plug it in. What we get is that this value is equal to the sum over all of my n data points of AKI, which we have, we read this off from the kth eigenvector of the kernel matrix constructed on the n data points, times the kernel that I evaluate now using my new data point and all the old data points in my old data set. So I evaluate the kernel between a new incoming point with all the points in my n points in my data set. I multiply that kernel by the eigenvector I got from the matrix, the original matrix K, sum it up, and that's my projection now. Okay, so let's look at an example of this. So here we have a data set in 2 dimensions, and the 3 rings are color-coded just for visualization purposes. Now, if we wanted to project this 2 dimensions into 2 dimensions using PCA, there would be no projection. We would simply have every data point is equal to itself, essentially. Perhaps there would be a rotation, but the data would essentially have the same relation to each other. Now, if we want to somehow separate these 3 rings from each other, what we might want to do is take these data points and project it into a higher dimensional space, and then do PCA there. And then that's going to allow us to perhaps separate these 3 rings from each other. And so here's what we did. That's what we did here. So what these plots are showing is taking each of these data points and calculating the kernel matrix, the pairwise kernel matrix using a Gaussian kernel, and then using that n by n kernel matrix and projecting onto its first 2 eigenvectors and eigenvalues. And we get something like this. And so, of course, depending on the kernel width, you'll get different results. I'll just focus on this term, which has a good kernel width. And what we see is we took each of these points and mapped it into a much higher dimensional space that corresponds to the Gaussian kernel, projected it back down into the same 2 dimensions, and we've essentially unwrapped our 3 rings here. So we've actually projected from R2 back into R2, except in this projected region, we went up to first an infinite dimensional space to then project back down into R2, and we've unwrapped our data. So there's some, before I end this lecture, I want to quickly discuss some areas of research that use this. So what we've done is closely related to something called spectral clustering. So that's where clustering maybe in this space isn't as good as clustering in this space, because we want to perhaps cluster the rings together. So in this way, we can cluster these 3 rings together more easily than we could here. It's also an example of something called manifold learning. And so this would be an example of a manifold that we want to somehow unwrap so that Euclidean distance, while used in this space, is not ideal. Euclidean distance in this space somehow is more useful. So k-means clustering here with 3 clusters would not learn the 3 rings, but perhaps k-means clustering here would learn these 3 parts right here.